Hi there, and welcome to our conversation about like dissolves like. And I will tell you that before you watch this video, you do need to make sure that you have already completed the atomic hookups assignment from week 7. It was a crash course video that you were supposed to watch and then answer some questions that introduced the idea of bonding. If you haven't watched that yet, then you should definitely go back and do that before you complete this assignment because it's going to build off of that information. And we're going to take a small amount of notes. And if you remember, on week 7, so like not last week because we didn't have class, but the week before, I did hand out to you a paper that looked very similar to this. The top half is for you to take these notes that I'm about to give you. So if you want to pause the video and grab that really quick, that would be awesome. And then we will get started. Okay. And so the first thing that I want to have you do is recall what you learned from that video. And that's the reason that atoms form molecules in the first place. If you remember, in previous weeks, we spent a lot of time talking about how atoms want to be more stable, and so they will gain or lose electrons in order to do that. There's also other things that they can do, like share their electrons. But regardless of how they go about doing it, atoms cannot achieve that stability alone. They have to work with other atoms that are also seeking stability. So they will bond together and then form molecules and compounds. And there are a couple of different types of bonds, but regardless of the type of bond, I do really want to make sure that you understand that a bond is not something that is made up of atoms. It's actually a force of attraction that's between atoms. So it's really actually energy. Okay. The two types of bonds that we're going to be mildly concerned with in our class this year are ionic and covalent bonds. There's a third type called metallic bonding. And if that's, if you're at all interested in chemistry, definitely go look up metallic bonding and read a little bit about that. But for now, we're only going to focus on ionic and covalent bonding. Now, we talked about ionic bonding in class because we are learning how to write formulas for ionic bonds. We know that in an ionic bond, as the name ionic suggests, an ion is formed, which means that there has to be a transfer of electrons, right? One atom has some to give away, one atom needs some, so they essentially meet each other's needs. When those electrons are transferred, we form oppositely charged ions, and those are, of course, attracted. And that attraction is a very strong and powerful force. Then there's also covalent bonds, which we did not talk about in class, but were mentioned in the atomic hookups assignment. In a covalent bond, what you have going on are electrons being shared. And so two atoms or, some number of atoms will come together and they will both be in need of an electron or two. And so they will share the ones that they have. And what you get is an attraction that occurs between the nucleus of one atom and all of the electrons that are kind of being shared in the situation. So either way, it's definitely an attraction. Now, there are a couple of different kinds of covalent bonds. And the way that you determine the type of bond, of course, has to do with the type of atom. And we're not going to spend very much time on that this year, but I just want you to be aware of that idea. In ionic bonds, you have a metal and a nonmetal. That's how we get the opposite ion situation going on. In a covalent bond, you have two or more nonmetals. So in order to figure out the type of covalent bond that you're dealing with, you're going to look at the difference in electronegativity. And electronegativity is basically how attracted an atom is to electrons. When you have an atom in a molecule that is really more attracted to the electrons, has a higher electron affinity, we did use that word in class, it's going to pull unequally on the electrons. And so it will create a different kind of covalent bond. So there's actually two different types of covalent bonds that you can see. There's a polar covalent bond and a non-polar covalent bond. In a polar covalent bond, the electrons are shared unequally, like I was talking about. And what that does is it creates poles, hence the name polar. And a pole exists because one end or one side of the periodic table, one side of the compound is partially positive and then the other side is partially negative. And so that molecule can act an awful lot like an ionic bond, which has a full partial and a full negative situation going on. Then you can also have non-polar bonds where the electrons are shared equally. So there's not a difference in attraction, so they lay just right in the middle. Now, in normal years, we spend a little bit more time on this idea. I ask you a lot more questions about this. For now, what I really want to make sure you understand is the importance of knowing the type of bond that exists in an atom. And the first reason we need to know the type of bond that exists in a molecule is because it helps us identify, it helps us to name and write the formula. You name and write formulas for ionic bonds differently than you do for covalent bonds. Now, again, this year we're only going to focus on ionic bonds, so it won't become an issue. But in your future chemistry classes, you will need to be able to identify something as ionic or covalent so that you can name and write its formula correctly. Okay. The other reason we need to know what type of bond a molecule is exhibiting is because it helps us determine shape. Remember that we talked about how electrons and their arrangement help determine the properties. Well, what a molecule is doing with its electrons also helps determine the properties. So the shape of a molecule is going to contribute to properties. Now, one of the most important things that I want you to learn in this class, one of the real life applications of chemistry, is this idea of like dissolves like. This concept goes back to the shape that we were just referring to. So molecules that are similarly shaped, so say two nonpolar molecules or two polar molecules, or even an ionic molecule and a polar molecule, they're able to mix together, or we could say that they're able to dissolve. Now, who cares about that? How does that apply to anything? Well, it actually applies quite a bit in your everyday life. I'm sure you guys are all familiar with the fact that oil and water don't mix, right? It's why you have to shake your salad dressing. And the reason that they don't mix, that they can't dissolve together, is because oil is nonpolar and water is polar. So the molecules are more attracted to themselves than they are to each other, so they won't stay mixed together. In your everyday life, if you don't like salad dressing, then this is an explanation for why we use different molecules for cleaning different substances. So, for example, have you ever got gum in your hair? A very common way to get gum out of your hair is to rub peanut butter into it, because gum is a giant molecule, and so is peanut butter. They're similar in shape, and so if you mix the peanut butter into your hair, into the gum will start to dissolve out, and then you can just wash out the peanut butter. Peanut butter isn't as sticky. Okay, so that idea that if you know the type of bond that a molecule has, or you know the general shape that it has, then you can figure out what you could use to dissolve it. Right? Or vice versa. If you are, working with chemicals like we're going to do in our lab that you did a pre-lab for, if you can identify what it's mixing with, you can make some predictions about the type of bond that it exists, or that exists within the molecule. Now, this idea also explains why soap is necessary to clean greasy dishes, and why soap and washing your hands with soap is an extremely effective way to fight viruses. And so one of your assignment that's going to go along with these notes is you're going to read a little bit about and watch a little video about how soap and the current coronavirus are related, or how soap kills the coronavirus so effectively. And it has to do with the fact that soap has a very similar molecular shape to the outside of the coronavirus, so it can dissolve it, whereas just pure water can't. Okay. Now, at the bottom half of that page, I put a little bit of information about an experiment, and this is very similar to what we're going to do in class next week. And so we have some students who went through and did an experiment, and they were trying to identify whether or not molecules were polar based on what they mixed with. So they took 5 different samples, A, B, C, D, E, and F, and they mixed them with water and then also something called heptane. I'm assuming most of you aren't very familiar with heptane, so you wouldn't know right off the bat that heptane, or the polarity of heptane, so we're going to try to figure that out. But everybody should know that water is polar. I feel like that's a concept that you maybe even possibly talked about in biology. Okay, so we know that water is polar. Okay, so if we apply this rule of like dissolves like, then a substance that mixes with water would then be polar as well. Since water is polar, then the substance that mixes with the water would also be polar. Okay, so we can experiment and mix things together with water and see if they will dissolve. And so that's exactly what these two lab students did. They took 5 different substances and they mixed them with water and they mixed them with heptane, and here are their results. They did use the fancy term for mixing, which is miscible. When you can mix two things together, that means they're miscible. If they don't mix together, so you get two distinct layers, like you see in your salad dressing, then we say that they're immiscible. Okay, so let's go through and let's look at this. So substance A was miscible with water and immiscible with heptane. So since it mixed with water and water is polar, we can say that substance A is also polar. Now, substance B would not mix with water. It did mix with heptane, right? So since it does not mix with water, we know that it's not similar in shape. So we can therefore say that it is non-polar, okay? Now, substance C was kind of exciting. It actually dissolved in both water and heptane, and this is something that can happen. Soap does this. It can actually mix with greasy substances and it can mix with water, and that is because it has both a polar and a non-polar end. Molecules that are really big can have one side that'll act like a polar molecule, and then they'll have another side that'll act like a non-polar molecule, and that's what we have happening here with C. All right, substance D would not mix with water, but it did mix with heptane. Since it won't mix with water, we know that it's not similar in shape. So that means that substance D would be nonpolar. And then finally, substance E, you can see, is miscible with water. So therefore, since it does mix with water, it must be polar, and it did not mix with the heptane. So it's definitely just going to be polar. Okay. Now, the other question then is, what is the polarity of heptane? Well, as we can see, substance A would not, which we decided was polar because it would mix with water, would not mix with heptane, right? So without looking at any of the other substances, we can conclude that heptane must be nonpolar. Again, remember that in order for two substances to mix, to be miscible, they have to be similar in shape. So polar dissolves polar, nonpolar dissolves nonpolar, right? So we're going to go ahead and declare that heptane is nonpolar, okay? So that experiment that we just walked through is actually very similar to the experiment that you'll be doing next week in class. So just keep that referenceable. And then the last thing that was on this page was just something for you to think about question-wise. I'm sure everybody in here has eaten spicy food before, right? And of course, if you didn't know this, this might change your life, but if you eat something very, very spicy, the best way to relieve the pain from that spice on your tongue and in your mouth is to drink milk or to have something that has a high fat content dairy. So things like ice cream or sour cream or yogurt would all work. And the reason that we drink milk after we eat something spicy is because the protein in milk is very similar in shape to the spicy molecule. They're both fat soluble. And since they are very similar in shape, if you get it all over your mouth, if you take a big drink of a fatty milk, so like whole milk or 2% milk, or take a big bite of sour cream, then that sour cream or that milk can dissolve that spicy molecule. And when you swallow it, it'll go down into your stomach. And then you have other things down there to help take care of relieving that pain, right? If you take a drink of water, the water does not relieve the spice. Now, if your water is really cold, then your tongue might just be feeling the temperature change, and so it'll give you temporary relief, but the spice feeling will come back. The fire of the spice will come back. It just sort of spreads it around in your mouth. It doesn't necessarily wash it away. And that's what happens again with the milk. Since they're similar in shape, the milk can dissolve the spicy molecule, and it can take it down into your digestive system. Okay, so that's a real life application of this idea that like dissolves like. So what you need to do now is take a picture of your notes, right? If you didn't get them taken, go ahead and go back and get them all written out and then submit that on Google Classroom. And now you're going to go and, as promised, watch a short little video about soap and the coronavirus and also read a short little article about it, which will explain why it's so effective at killing that virus and really any virus, and why alcohol-based hand sanitizer is a good second alternative if you don't have soap and water available.